Good morning, students. So today we are going to discuss on rigid rotor or rigid rotator. Both are the same. In some other books you may find rigid rotor. In some other books you may find as rigid rotator. So this is a three-dimensional model. So this is a continuation of our models. We discussed in the last class about hydrogen atom, in which we used spherical polar coordinates, 3 coordinates, r, theta, phi. Using the techniques of separation of variables, we separated all the 3 coordinates r, theta and phi. R stands for radial part, theta and phi stands for polar coordinates. Okay, theta stands for the angle, polar angle. Your phi will be azimuthal angle. So we separated, and we could calculate the wave function and corresponding energy eigenvalue of the hydrogen atom. So that was our target. The similar thing that we are going to discuss, the same thing. Here also we are going to use separation of variable technique, and we are going to separate the variables. Here also we are going to use spherical polar coordinates. But in fact, so this is the model. So rigid rotator is a model. It's a linear model. We have two masses attached with a bond. So it's exact like a thread. Two masses is like a spring. So it's linearly it is attached. Okay. So this distance between these two atoms are fixed. The distance between these two atoms is fixed. Correct. So we are not going to vary the radial part. So we are going to vary only theta and phi part. Okay, is it clear? So in the earlier cases, we varied all the 3 coordinates, r, theta, phi. But in this case of rigid rotator, we are going to vary only theta and phi. Okay, because two masses attached with a small thread-like thread or bond, and this is about this. You have a center of mass about which the perpendicular line will be there. So these two masses will rotate. Okay, so this is what the idea is. So we are going to vary theta and phi. Okay, so we have the equation, and in which that will contain only theta and phi. We are going to use same technique, separation of variables, and we are going to separate theta and phi part, get the solution. And of course we are going to calculate the energy eigenvalue. This problem mostly it is used only in chemistry, most probably. Chemistry, they will find out rotational energy and vibration energy of molecules. And especially this is exactly we can compare with a diatomic molecule. So we have 2 molecules, it's a diatomic molecule attached with some bonds. Okay, so it is exactly. Also it can be, this is for linear diatomic, correct? So we can also have 3-dimensional molecules also, like for example water molecules, methane molecules, ammonia molecules. So these are the examples for 3-dimensional model. Okay, so we'll discuss rigid rotator in detail. So our idea is to find out the rotational energy of the diatomic molecule, and also we are going to find out the energy eigenvalue, as well we are going to find out the wave function. Okay. So rigid rotator is a system of 2 spherical masses, m1 and m2, situated at a fixed distance. So this is fixed distance. It can also have free distance also. So fixed distance as well free distance. Free distance means we can vary the distance between these 2 atoms. So that's called a free axis. This is fixed axis. Okay. In fixed axis we are going to find out the rotational energy. In free axis we can find out the vibration energy. Okay, at a fixed distance and from the center of mass. Center of mass we know already. Okay, center of mass of the system. It is capable of rotating about an axis, passing through the center of mass and perpendicular to the plane containing 2 particles. Okay, so this is the idea. So this is your center of mass. Okay, this is the center of mass. This is mass 1 and this will be your mass 2. The distance between these two, from the center of mass to m1 will be your r1, and this one will be your r2. The total distance will be r, which is equal to r1 plus r2. And of course, M1 R1 must be equal to M2 R2. So this is the idea. So what is the definition for rigid rotator? So rigid rotator consists of two mass points M1 and M2 attached at the two ends of massless rod. Okay, the system is capable of rotating about an axis passing through its center of mass perpendicular to the length of the rod. Okay, so examples we know already. This is about the diatomic molecule. We are going to get the rotation energy of the diatomic molecule. So this is the idea. Now as I said already that M1 R1 equals M2 R2 according to the diagram, and also R equals R1 plus R2. So M1 R1 equal to M2 R2, so we can have R2 equals M1 by M2 and R1. You substitute here in this equation. So this becomes R equals R1 plus, instead of R2 you just substitute M1 by M2 R1. Take the LCM. We will take the LCM. So M2, so you have M2 R1 plus M1 R1 divided by M2. You pull R1 out. So that will give you M2 plus M1 divided by M2. Now we need to have R1. So R1 becomes M2R divided by M2 plus M1. Similarly, you can get the expression for R2. R2 equals M1R divided by M2 plus M1. How to go with? So you will have to go with R1 equals M2 by M1 R2. Then you substitute here. You will get the same expression. So we have come to know R1 expressions for R1 and R2. Okay. Now we know that the moment of inertia of the system. Of course, we have the moment of inertia. You have mass and you have distance r is there. So it's a rigid body. So we must have moment of inertia, which is nothing but sigma m ri squared. We would have studied earlier. So I equals m1 r1 squared plus m2 r2 squared. Okay, we have already got the expressions for r1 and r2. Substitute in this expression. So I equals m1 r1 squared. Okay, this is your r1 squared. So r1 squared plus m2 r2 squared. So just to square it. So we have m1 m2 squared r squared divided by m2 plus m1 whole square. Okay, plus m2 is here, m1 squared r1 squared divided by m2 plus m1 whole square. Again combine these two expressions. So you will have m2 plus m1, it's a common term, m2 plus m1 whole square. So this can be written as exactly like this. Okay, m1 m2 squared r squared plus m2 m1 squared r squared. So pull it out, r squared as common. Now you just take m1 m2 out from the numerator. So m1 m2, the remaining will be your m2, the remaining here will be m1, and this m2 plus m1 and this one will get cancelled. So you have only m1 m2 divided by m1 plus m2. Okay, so that's for your I. So I equals your m1 m2 divided by m1 plus m2 r square, which is equal to the mu r square. So mu stands for reduced mass. Okay, we know already 1 by mu equals 1 by m1 plus 1 by m2. So your mu, the expression for mu will be given by this. So here interacting system of two interacting particles can be reduced into one particle equation. So this is for one particle. If you use mu, we are going to use one particle equation. So two particle equation converted into one particle equation because of this mu. Okay. Now as I said already, the two masses, the distance between two masses is fixed, or it can be varied also. So if it is fixed, this is called a fixed axis. If it is varied, this is called a free axis. So most probably we will calculate the rotation energy, and here it is vibration energy. Okay. Consider two masses replaced by the reduced mass m at a distance r from the axis of rotation for one equation. Okay. Generally, the potential of the rotating dumbbell, this is called dumbbell shape. Okay, is 0 because r is fixed. R is fixed, the potential energy will be 0. So your potential energy will be 0. Okay, as the point masses are rigidly connected with a massless rod which does not change its length because it's fixed. So due to rotation, here the distance between the two masses remains the same during the rotation. We know already because it's fixed. The rigid rotator has the angular momentum L equals I omega. So we know already. Okay. Now, as we said that total energy, kinetic kinetic energy plus potential energy, total energy. Potential energy equal to 0. So your kinetic energy only will be half I omega square. Okay, because this is a rotation. Okay, it's not linear, it's a rotational kinetic energy. So E equals half I omega square. And we know that L equals I omega, correct? So your omega squared will be L squared divided by I squared. So substitute in this equation. So you have E equals 1 by 2 I multiplied by, instead of omega squared, L squared by I squared, which is equal to L squared by 2I. So we know that the angular momentum should be an integral multiple of h bar. Angular momentum L is the integral multiple of h bar. So L h bar, we know already. So our angular momentum is the integral multiple of L h bar. Okay. So therefore we can write L equals L h bar. Of course L equals I omega, we know already. So omega equals, now omega equals L h bar divided by I. So we know already E equals 1 by 2 I omega squared. So your omega equal to L h by I, substitute here, you will get E equals L squared h bar squared divided by 2I. So I squared and I, that one I will get cancelled. You have L squared by h bar squared divided by 2I. So this is the energy, the expression for the energy. Now look at this expression. L is a discrete quantity. Okay, L is quantized because L goes from 0, 1 to n minus 1. Okay, L is the orbital quantum number. Okay, number is a discrete one, it's a quantized one. If L is discrete, E must be discrete. So we will have only discrete energy. This expression and this discussion was carried out by Albert Einstein in the year 1911 in Solvay conference. He presented this paper. Okay, in Solvay conference, he presented first time about the rigid rotator, about the diatomic molecule. The extension was done by Schrodinger. Okay, the extension maybe after 10 years, 10-15 years. So this was done by Schrodinger, 1926-27. Okay, so it's clear that energy is quantized. The energy of the rigid rotator is quantized. So it's very clear. It is not continuous, it is discrete. Okay, now we'll go for the wave function. So we have already computed the energy eigenvalue, energy values, and we are going to see on the wave function and the permitted energy levels of the rigid rotator. And we are going to use time independent Schrodinger wave equation, correct? So as usual, we are going to use this equation. And as we said already, this is the 3-dimensional one, and we are going to use spherical polar coordinates. So we will have to use only this equation. Okay, so spherical polar coordinates. Using spherical polar coordinates, the Schrodinger wave equation is given by this expression. Okay, so this is your radial part. This will be your theta and phi parts. Okay, angular parts. Okay, that will be your energy term. And of course, we discussed just now that potential energy V equals 0. Just now we said. Okay, and also we discussed about the radial part, which is also equal to 0 because this is fixed. So we are going to omit this part and also V part. So remaining part depends only on theta and phi, correct? The remaining part depends only on theta and phi. So theta and phi we can separate easily. Okay, the earlier classes we separated all the 3 coordinates. So now we are going to separate only 2 coordinates, theta and phi. So we are not going to have this radial part, no more. Okay. The wave function, which is psi, which is a function of r theta phi, function of r theta phi. For a rigid rotator, there is no potential energy. Just now we said. So psi is independent of r. So the radial part also will become exactly 0. So it will be 0. There will be no potential energy. Okay. So it depends only on theta and phi. So together, what we call this as spherical harmonics, YLM theta gamma phi. Okay, so together the wave function becomes YLM theta gamma phi. Okay, so we have omitted now radial part, we have omitted now the potential energy also. So remaining term of Schrodinger equation in spherical polar coordinates has been written here as equation 2.304. Any doubt? So wave function psi can be written as spherical harmonics, which depends on theta gamma phi. So instead of psi you can write y theta phi. Okay, instead of psi we have written y theta phi. Is it okay? Equations. Now multiply throughout by r square. Multiply throughout by r square. This r square will get cancelled. Here also r square will get cancelled. You have 2m r square. correct? But we know already I equals sigma mi r I squared, we know already. So I equals mr squared. So instead of mr squared, you can write I. So in the next equation, we are going to write I. Okay. Now we are going to use the techniques, separation of variables. We are going to separate two equations as theta part and phi part. So we know the technique YLM theta comma phi, which is the product of theta and phi. Okay. So we know already this one, product of polar angle and azimuthal angle. So now we are going to substitute. So instead of y theta comma phi, we are going to substitute theta and phi. Okay, so the same thing here we are going to write theta comma phi, here theta comma phi, here also we have theta comma phi. Any doubt? This we have brought from left hand side to right hand side, that's why minus sign exists. Any doubt? Okay, so now you multiply with sine square theta divided by theta comma phi. So here phi is constant, you pull it out, correct? Because it depends only on theta. So you pull phi out, multiplied by sine square theta divided by theta comma phi. Already one sine theta is there, so you will have sine theta. That will get cancelled. You have sine theta. So this phi will get cancelled. You have 1 by theta. So sine theta divided by theta, partial d by d theta, sine theta, d theta by d theta. Any doubt in the first part? So multiply by sine square by theta phi. So this sine square will get cancelled. You have theta phi. As we said that theta is a constant. Okay, it depends only on phi. You pull it out. So theta divided by theta phi, d squared phi by d phi squared. This theta will get cancelled. You have 1 by phi, d squared theta by d phi squared. See now, this is independent of theta. Okay, this phi will cancel. This will be independent of phi. This is independent of phi. This is independent of theta. So we have separated almost. So which is equal to 2ie theta phi divided by theta phi will cancel. So 2ie by h bar square sine square theta. Of course, sine square theta also exists. Okay, we can simplify. Doesn't matter. So we can bring that term. Okay, this term to right hand side. We will have this term. So we have separated easily. Okay. So fully depends only on theta. That depends only on phi. So we have separated theta part and phi part. Two different equations with different coordinates. That's called the separation of variable techniques. So it depends only on theta. It depends only on phi. So which is equal to some constant, which is nothing but your magnetic quantum number. So ml square. Okay. And of course we know the solution already. We have discussed earlier in two classes, d squared phi by d phi squared plus ml squared phi equal to 0. The solution of this differential equation is given by this expression. Phi m equals 1 divided by root 2 pi e power I ml phi. We know already. Okay. Now we will go for this theta part. So you have theta part which is equal to ml squared. Okay. Now divide throughout by sine square theta. So you will have 1 divided by theta sine theta. One sine square will, okay, one sine theta will get cancelled. So you have 1 divided by theta sine theta d by d theta sine theta d theta by d theta plus 2ie by h bar square sine square theta sine square will get cancelled. You have ml square divided by sine square theta. You bring this term to here, okay, from right hand side to left hand side. Okay, multiply throughout by theta. Multiply throughout by theta. So you will get the complete expression now. So multiply throughout by theta, that will give you, this theta will go here. Okay, we are going to take this one as lambda. Lambda equal to 2ie by h bar squared. 2ie by h bar squared we are going to take it as lambda. So lambda minus ml square divided by sine square theta of theta, which is equal to 0. Okay. Okay, where lambda is given by this expression, and of course we know lambda equal to L into L plus 1. We know already. So simplifying this, we need to have only E. So E equals L into L plus 1 h bar square divided by 2i. Okay. In the earlier case, it was E equals, can you remember? E equals, come on, in the earlier case, E equals L squared h bar squared divided by 2i. So now this is E equals L into L plus 1 h bar squared divided by 2i. Suppose if there L equal to 0, E will be 0. Here also L equal to 0, E will be 0. L equals 1, L equal to 2, we have all discrete values. So it's also quantized. Okay. So this is the permitted energy levels of the rigid rotator. Thus the energy eigenvalues of the rigid rotator depends on L. L alone, here L alone. For each L greater than 0, there are 2L plus 1 values. Suppose if it is L equal to 1, we have L equal to 1 means we will have 3 values. Correct? We will have 3 values. 3 values of M. So M equals 0 plus or minus 1 plus or minus 2 plus or minus 3 goes on. The above equation represents the allowed energy values of the rigid rotator with free axis. Correct? So the eigenfunction YL and theta comma phi for the rigid rotator is a solution of equation 2.311. So this is 2.311. Okay, this phi part, and 2.314 this equation. Okay, the solution of this differential equation already we discussed in the last class. This is about the Legendre differential equation, so Legendre polynomial. Okay, so we know already the solution of phi part is given by the product of this and solution of this will be the complete solution of your spherical harmonics. So that's the N. So this is the wave function, and this is your energy eigenvalue of a rigid rotator. Okay, complete wave function. So this is what the target is. Okay, any doubt? So now we will try to solve the 3 problems. Problem number 1. We are going to use only the energy values of a rigid rotator. Okay, calculate the energy difference between the first 2 rotational energy levels. So first 2 rotational energy levels. So it means L equal to 0 and L equal to 1. First 2 rotational energy levels of CO molecule. If the intermolecular separation is given by 1.31 angstrom, the mass of the carbon atom is given by this one, and the mass of the oxygen atom is given by this one. So assume the molecule to be rigid. So the energy value of rigid rotator is given by this expression. We know already. So as I said, first 2 rotational energy levels. So E0, L equal to 0, and E equals EL. So L equals 1. L equals 1. So when L equal to 0, your E0 will be 0. We know already. So E1 is given by 1 multiplied by 1 plus 1 divided by 2i h bar square. So that will be your 2 h bar square divided by 2i. 2 gets cancelled, you h bar square divided by I. So what is asked? The energy difference is asked. So del E is asked. So del E equals E1 minus E0. You just subtract this one. You will have h bar square by I minus 0, which is equal to h bar square by I. Moment of inertia. Okay. So del E equals h bar squared I. We know already I equals mu r squared, we know already. Correct? So mu is given by m1 m2 by m1 plus m2. m1 is here, m2 is there. So mu equals, you substitute for m1 m2 divided by m1 plus m2 and simplify, you will get the value for the reduced mass mu. And of course I equals mu r squared. So mu multiplied by R is given. R is given as intermolecular separation 1.131 angstrom. So which is here. You just multiply, that will give you 14.5616 into 10 power minus 47 kg meter square. So this is your moment of inertia I. So del E equals h bar square divided by I. So del E equals h bar square divided by h bar the value, and this is the value for your I. Simplify, you will get 7.63 10 power minus 23 joules. Okay, del E. You can convert this one into electron volt also observation. Okay, doesn't matter. Is it okay? Simple problem. Now problem number 2. Calculate the energy difference between the stationary states L equal to 1 and L equal to 2. So again we have 2 states, L equal to 1 and L equal to 2 of the rigid molecule H2. So hydrogen molecule. Use the Bose frequency rule. So we are going to use Bose frequency rule to estimate the frequency of radiation involved during the transition between these 2 states. Okay. So we know that the expression for energy of the rigid rotator is given by this expression. So it's given as L equals 1 and L equal to 2. So your L equal to 1 means E1 equals h bar square divided by I. Correct? You substitute for L equal to 1. You substitute for L equal to 2, you will get wells. Okay? You will get E2 equals 3 h bar square divided by I. You will get 6. 6 divided by 2 will give you 3. So 3 h bar square divided by I. What is Bohr's frequency rule? Which is nothing but nu equals E2 minus E1 by h. Okay. So E2 minus E1 is given by, you just subtract this one, 3 h bar square minus h bar square will give 2 h bar square divided by IH. Okay. H. E equals h nu. That is Bohr's rule, not h bar. Okay. Bohr has taken from Planck's idea. E equals n h nu. Okay. This is h nu. So that's why it has come as h. So I equals mu r square as usual, and it's given as the molecule masses of the molecule, hydrogen molecule. It will be the same. So that's why we written as m divided by m plus m. Okay. Okay. So r square. So this will be, you will get m square divided by 2m. M cancel. You have m by 2 r square. Okay. This expression for your I. You substitute here. So you have nu equals 2 h bar square divided by m by 2 r square h. That will give you simplify, that will give you 4 h bar divided by m r square. So nu equals 4 h bar divided by m r square. Okay. I think we have converted into h bar. Okay, we'll see. So problem number 3. Calculate the number of revolutions per second which is a rigid diatomic molecule makes when it is in the state 2 states, L equals 2 state, and another one will be L equal to 5 state, 5th state, given that the moment of inertia of the molecule is I. Okay. The energy of the rigid rotator is given by this expression, we know already. Now we are going to compare with the classical rotation energy. Classical rotation energy is given by E equals half I omega square, classical one. So you have EL equals half I omega square, on omega equal to 2 pi nu. So you just substitute for omega, which is equal to omega square will be 4 pi square nu square. You just shake it up, that will give you 2 pi square I nu square. Okay, that will be your classical. You compare these two. So one is classical, another one is quantum. So you compare these two. Okay, so you have nu square. You can get the value for nu square. Okay, we can get the value for nu square. Calculate the number of revolutions it's asked. Nu stands for number of revolutions. Okay, it's a frequency. Okay, that's why it's nu square. So keep nu square and remaining terms and all to right hand side. So we'll give you nu square equals L into L plus 1 h bar square divided by 2i multiplied by 2 pi square I. That will give you 4 pi square I square. Take the root. So your nu will be root of L into L plus 1, your h bar divided by 2 pi I. Okay, now we'll go for 2 states. L equal to 2. Substitute L equal to 2 there. You will get nu equals h bar root 6 divided by 2 pi I. Okay, now we'll go for the next state, L equals 5, and substitute for L equals 5, you will have nu equals h bar root of root 30 divided by 2 pi I. Okay, so that is the end of this second unit. Okay, so we have finished the last one, which is nothing but rigid rotator. Okay, so thank you students. Bye, we'll see you later.